Hey, what's up everyone? Welcome to today's presentation on weak heaps. Before we get to know about weak heaps, first let us know a little bit about history of weak heaps. Weak heaps were first introduced by Professor Ronald D. Dutton from University of Central Florida in 1993 as a part of variant heap sort algorithm that could be used to sort n items using only n log n plus O of n comparisons. They were later investigated as more generally applicable priority queue data structure. So what is a weak heap? In computer science, a weak heap is obtained by loosening the requirements of a binary heap, or in other words we can say a weak heap is a data structure for priority queues combining features of binary heap and binomial heap. And this weak heap has several properties. If a heap satisfies the below three properties, then such heap is a weak heap. So now let us take a look at these properties one by one. So the first property says that weak heap, the value in any node is at least the value of any node in its right subtree. So this basically means that the root value is greater than or equal to any value which is present inside the right subtree of a weak heap. Alright, now second property says that the root has no left subtree. The weak heap, the heap which doesn't have any left subtree, then such heap is called weak heap. And now finally the third property is nodes having fewer than two children except the root node appear on the bottom two levels of the tree. Alright, now let us take a look at how a typical weak heap looks like. So here we can see this is how a weak heap looks like. So here the root value is greater than or equal to the values which are present in the right subtree. Okay, so this is greater, so this is satisfying the first property. And the second property is this weak doesn't have any left subtree, so it's totally empty, so there is nothing here. Alright, so that's the second property. And the third property is nodes having fewer than two children except the root node appear on the bottom two levels of the tree. So here we can see all these nodes appear at the bottom two level of the tree. Alright, so what makes weak heap weak? Well, there are some distinguishable properties of a weak heap. The first one is it can be imperfect when compared to a binomial tree, whereas binomial tree should be perfect. Okay, in the second property, it says that in contrast to regular heaps, weak heaps do not require that all of the bottommost nodes be as far to the left. So this is one of the most important properties when we are dealing with regular heaps. And the third property says that it is a single tree, counter to binomial queue, which is the collection of perfect trees. And the fourth property says that each node's left subtree values are completely unrelated to its parent. And the fifth property is it's fairly balanced. Alright, so now let us take a look at how to merge two weak heaps. First, we check which weak heap has a greater root value, and we make that value a root node of a final weak heap. And then we make the second weak heap a right subtree of the final weak heap, and finally we make the right subtree of the first weak heap a left subtree of a second merged weak heap. I know it's a little confusing. We'll see that in action in a while. So this merging is very important because we need to know this in order to sort an array when we are dealing with weak heaps. Now let's take a look at how to merge two weak heaps. Alright, so here we can see there are two weak heaps. Now the first step is to compare the root nodes of these two weak heaps, which is greater. So here we can see 35 is greater than 25. So what we do is we take this root node and we will place it here, because this is going to be the root node of the final weak heap. And the next step is to take this weak heap and place it here, and this is going to be the right subtree of the final weak heap. Alright, I'm going to link this, and the final step is to take this whole heap and place it here and make this heap the left subtree of the second weak heap. So now that's how you merge two weak heaps. Okay. How to represent weak heap using an array? The structure can be implemented on a one-dimensional array with one extra bit per data item, and can be initialized with n items using exactly n-1 data element compares. In other words, if the number of elements in weak heap is n, then the length of array should be n plus 1. In our case, the weak heap has 8 elements and the array has length of 9. And also, for any weak heap, we can find its left child by using the equation w. W is the name of an array, so that's going to be w of 2 times index, and the right child can be found using the equation w of 2 times of index plus 1. Okay. So here we can see the weak heap array representation, and these are the index values in which these values are going to be placed. So 35 index is 0 and 25 is 1, and we are going to be representing an array using representing weak heap using an array by breadth first search algorithm. So here we can see 35 should go to 0th position, so 35 is in 0th index, and 25 should be in first index, so it's at first index. 20 should be at second index, 15 should be at third index, 28 should be on fourth index, and 14 should be on fifth index, and 24 should be on sixth index, and finally 14 should be on 7th index. And left child, for any given node, we can find its left child and right child using these equations. Now let us assume that we want to find the left child and right child of this node. So to find the left child, what we do is w of 2 times of index, so that's going to be 2 times of index value is 1, so 2 times 1 is 2, so that's going to be 20 is the left child, and the right child is 2 times of index plus 1, so 2 times of 1 is 2 plus 1, that's going to be 3, so this is going to be the right child. So here we can see the left child is 20 and the right child is 15. Now you might be wondering why there is an empty space here. Well, this empty space is used whenever we try to sort an array using a weak heap. Okay, so that's when it is used. Alright, now let us see how to sort an array using weak heap. So this is a weak heap. What we do is we take the root value of a weak heap and place it at the last position of an array. So 35 has been placed in the last position of a given array. So now the left out heap would look like this. Now what we do is we unlink these two branches. It's going to look like this. So 28 is here and 14 tree is here, and the remaining right subtree is here. And now what we do is we merge 28 again back to this tree. It's gonna look like this, and now we compare the root values of these two trees. So 28 is greater, and it's going to be the root node of the weak heap, and this going to be the right subtree, and this tree is going to be the right subtree of the final heap, and the remaining nodes, that is these two nodes, are going to be the left subtree of this node. And now we have a weak heap again. So what we do is we take this 28 and we place it in the second last position. Okay, and now the remaining heap would look like this, and now we unlink this branch now, and it's gonna look like this. And now we again compare the root value of these two trees, and we can see 25 is greater than 20, so that's going to be the root node of the weak heap, final weak heap. And then we take this tree and we are going to be making that as a right subtree, and the remaining values, that is 15, 24, 14, are going to be the left subtree of 20. And now we have again the weak heap, and we are going to be placing that, we are going to be placing this 25 in the last third position. Likewise, it's going to continue, and finally we are going to have an array which is sorted. So here we can see that this array is sorted. Now the question here is, why should we use weak heaps for sorting? What are the improvements does it provide? All branch swaps inside the array can be simulated by using the reverse bits. We saw this when we were trying to sort an array using a weak heap. And the second point says that the flexible or relaxed criteria prevents us from always having to bubble up, as in normal heap. In normal heap, if it's a minimum heap, we have to bubble up the minimum value to the top, or if it's a max heap, then we have to bubble up the maximum value to the top, but we don't have to do that here. So this is going to save us a lot of time, hence weak heaps are a little bit faster. Third point is, using that extra array position which we were talking about earlier, the entire sorting procedure can be completed locally or in place. Now the final analysis. Finally, theoretical analysis and empirical results indicate that it is a competitive structure for sorting. The worst case number of data element comparisons is strictly less than n-1 log n plus some constant multiplied by n, and the expected number is conjectured to approximately n-0.5 log n minus some constant times n. Alright, so that was about the weak heaps. I appreciate you all taking the time to watch this presentation on weak heaps, and I hope it was insightful, and thank you for watching this presentation.